Friends, you might remember that in the last episode we talked about how James Webb Space Telescope is better than Hubble and how both telescopes work to capture this deep space image. If you haven't seen the first part, you should watch that video. The link is in the I button above and the description box. Friends, this video is about James Webb's first colored image and what conclusions we can draw from looking at this image. At first glance, you won't notice much difference between Hubble and Webb images. Both are almost the same, but if we look in detail, we can see quite a lot. So let's start today's video on this note. Friends, we already covered point number 1 in the first part, which was about the performance of telescopes, so let's move ahead now. Point 2. Regions of the sky that seem like cosmic voids are not always truly empty. That means the parts of space that seem completely empty to us are actually not empty. By the way, we've seen this theory quite a while ago, where neither stars nor galaxies are visible. Scientists were surprised to see such large voids, wondering how this could be possible, how such a large part of space could be empty, whereas our universe's objects are quite far away, which due to our technological limitations remain a big mystery. In this situation, it was thought those objects might be hidden behind cosmic dust, which our telescopes are not able to see, and these voids are really empty. And these voids are real. Everything looked empty here, but in this image from Webb, we can see a lot of galaxies there. Yes, these regions are definitely underdense, meaning not many objects are found here, but they are not empty at all as was previously thought. James Webb not only found these objects, but also identified them separately and examined their properties. Meanwhile, Hubble wasn't even effective in observing these objects. One thing is clear from this: the more we look into space, the more we will definitely find something somewhere. This space is definitely not empty at all. Point number 3. This structure, our largest, most massive early galaxies, will finally be visible to us, meaning now we will be able to see the biggest and heaviest early galaxies. When you look through Hubble's eyes, the farthest object you can see appears very faint and blurry. That object looks just like a smudge in the picture. But if we turn our attention to this new image from Webb, we get to see a completely new view. In this image, we can literally see the farthest galaxies, and even just by looking at them, we are also able to detect their structure. We are able to identify stars and galaxies separately by their structure, which is a big deal. Here, you must be able to easily detect both nearby objects and distant objects. The main galaxy cluster that this image focuses on is Southern Massive Cluster Survey 0723, which according to calculations is located at a distance of 4.6 billion light years. But you can easily see the objects redshifting in this image. Now, what is this redshift? Let's take a quick look at this first. When light comes from a very far distance and travels a long way to reach us, the energy of that light particle, that is the photon, during this journey, it keeps decreasing, and on the opposite side, its wavelength keeps increasing, or you can say that the wavelength gets stretched. Now look at this spectrum and notice that as we move towards the red color, the value of the wavelength increases on the spectrum. And the opposite is also true, that as the wavelength increases, we will see it as red color on the spectrum. You must have noticed that we often compare redshift with the Doppler effect, and for its physical significance, the example of an ambulance is given. When an ambulance comes closer to us, that is, the observer, the sound of its siren increases, and as soon as it passes by us, the sound of its siren starts to decrease. This is a perfect example of the Doppler effect, but this Doppler effect is observed due to relative speed. But if we talk about astronomical redshift, we observe it due to the expansion of space. In this image from Webb, all the galaxies that appear red to us are all redshifted, meaning those galaxies are very far away from us. This image at this point is also confirming another thing, that space is is indeed expanding, which is proof of Sir Edwin Hubble's observation and also of the Big Bang Theory. Hubble's law states that the greater the redshift of the light coming from any object, the farther that object is from us and the faster it is moving away from us. That means the space between us and that object is expanding just as rapidly. So if you look closely at this picture, you'll find several points here that have a very high redshift, which means according to Hubble's law, this galaxy is the farthest away and is moving away from us very rapidly because the space between this galaxy and us is expanding very quickly. So from here, this image also proves the expanding universe and Hubble's law. We know that accretion and mergers, these two factors decide how a galaxy will evolve over time. In astrophysics, accretion means the accumulation of particles into a massive object, that is, small particles coming together to form a larger object which then gravitationally attracts even more matter. Accretion disks mostly contain gases, and almost all astronomical objects like stars, planets, and galaxies are also formed through this accretion process. Only a few thousand years had passed since the Big Bang, and the universe had now reached a point where it had cooled down enough for atoms to form. Now atoms had formed, but due to the heat, the kinetic energy of the atoms was still very high, so the atoms couldn't stay in one place. But as the universe continued to expand and cool down, the atoms also lost their kinetic energy. It's believed the first proto-galaxy formed by combining with dark matter. As accretion continued, galaxies kept forming, and the accretion that happened inside the galaxies led to the formation of stars. However, we only have indirect evidence for this theory. Their birth happened in this way, but their evolution began with mergers. In this image, the more redshift we see, it's possible that we might see the earliest galaxies there, or we might see these galaxies evolving. We know that galaxies that are in a galactic group or clusters evolve differently in terms of shape compared to galaxies that are alone. This means isolated galaxies and galaxy groups evolve differently. If we want to track the evolution of galaxies, then this Webb image and many upcoming deep field Webb images like this will help us observe the evolution of these galaxies. But how? So we have to remember here that now we have 270 times more resolution, which directly means a 700% increment in the number of pixels. That means the galaxy, which appeared as 3 by 3 pixels in the Hubble image, will now appear as 8 by 8 pixels through the eyes of James Webb Space Telescope, allowing us to see the shape and configuration of galaxies over the period of cosmic time and according to their location. And with the help of these images, we will be able to see our universe growing up throughout its history. But do you know that there are also some imposters, and they become a big problem for us? But we will learn about them in the next part of this video. But if you haven't watched the first part of this video, do watch it. You will find the link in the description. Friends, we are trying to understand this image in great detail. Tell me the name of the oldest discovered galaxy in this universe. Yes, I know this question isn't that common. Many people might not know the answer to this, and some who do will say GNZ11 galaxy. But yes, if that's your answer, then you are both right and wrong, because there are many imposter galaxies roaming around in this universe. So before moving forward, let's find out a little bit about this video. This is the third part of understanding James Webb Space Telescope's first color deep space image. 2 videos have already been released before this, which you can watch by clicking on the I button above, and the link is also given in the description below. Earlier, we have already discussed 3 important points about this image, and today we will begin this video from point number 4, which is that means the period of imposter galaxies is about to end. Now, what are these imposter galaxies or Baharupiya galaxies? The very first question that will come to your mind is this. Let's search for the answers to all these questions and uncover the deep mysteries hidden in this picture. So, Mr. Janab, New General Catalog 11. This galaxy was our farthest known galaxy, which was located about 32 billion light years away from us. This galaxy was discovered in 2015 and it is believed that it came into existence 400 million years after the Big Bang. But in April 2022, scientists discovered another galaxy, which was a much more redshifted galaxy. It was named HD-1. This galaxy is considered one of the most distant galaxies ever discovered in the observable universe. It is 33.4 billion light years away from us, and it is estimated that it came into existence just 330 million years after the Big Bang. So the title of the farthest and oldest galaxy goes to the HD-1 galaxy, but the big thing is that it hasn't been spectroscopically confirmed yet. Yes, it's true that HD-1 looks completely red, and there are no shorter wavelengths in this light. The wavelength of the light coming from HD-1 has been completely stretched. If we pay attention to the redshift of HD-1, its redshift is 13.27. This means that the light coming from HD-1 has traveled through space for 13.27 billion years to reach us. But when the light coming from HD-1 was split and its spectrum was observed, only one absorption line was seen in that spectrum, from which we couldn't figure out anything. But if we had seen multiple lines in its spectrum, we could have determined how much redshift had occurred in the light due to the expansion of the universe. So here we can say that we didn't have any tool for legitimate spectroscopy yet, with which we could find out how far an object is and whether it is actually a galaxy or not. Just like HD-1, there is another candidate for the farthest object named HD-2, but the problem is that it doesn't have any spectral lines at all. Now, it is possible that the objects we consider to be the farthest galaxies, or they could be extremely bright stars. Besides this, they could also be quasars or pulsars, and these are called impostor galaxies, which look like galaxies to us, but in reality, they are not galaxies. Now, no matter which telescope the images are from, just by looking at any red dot, you can't say for sure that it's a galaxy. It could be any bright object which Hubble wasn't able to fully differentiate. But now, the James Webb Space Telescope can study every single entity visible in this image very well. Any of the red-shifted points visible in the background of this image could be a galaxy, or even an impostor galaxy. But by studying the spectral lines coming from those objects in detail, this telescope will be able to determine whether the object is really a galaxy or something else. As we know, the James Webb Space Telescope is highly sensitive to wavelengths beyond 2000 nanometers, so any galaxy that is highly redshifted can be detected by it. For example, let's take our record holder galaxies HD-1 and GNZ-11. Now, with the James Webb Space Telescope, both of these galaxies will be spectroscopically confirmed in a way that has never been done before. Just like we've already seen the first spectrum result from James Webb Space Telescope, and we can do this for all galaxies. By doing spectral analysis of every single point, every single object present in this image, we can confirm whether it's a star or a galaxy. Generally, we find two types of people in astronomy. First, there are those who make extraordinary claims based on just a hint and without any solid evidence, and then there are others who don't accept any extraordinary claim until there is solid evidence in its favor. We are now in the era of the James Webb Space Telescope, living in the age of James Webb. Now we have the capability to pinpoint any galaxy and get the evidence we need through James Webb Space Telescope without any difficulty. Now, this is not a big deal anymore. Every new James Webb image will set a new record. Now the time is gone when we would create new assumptions in the absence of evidence. Rather, now is the time when we see the truth and reality without any doubt. Thanks to James Webb Space Telescope, we are now in a position to say that we will replace "we believe." We know, and all this will only be possible with the help of James Webb. So first, let's find out what gravitational lensing actually is. When we look at gravity at an extreme level, gravity creates some really fascinating visual effects. The general theory of relativity tells us how a massive body distorts space and time around it. When light passes near that massive body, the distortion of space causes the light to bend as well. It's similar to how light passes through a convex lens. A gravitational lens is formed when a large amount of matter is concentrated in one place. For example, when light coming from behind galaxy clusters passes near them, the distortion of space bends the light in such a way that it magnifies the star stars and galaxies that are located behind the galaxy cluster. This effect is exactly like what we see when we look through a magnifying glass. This effect brings out the details of those galaxies that are extremely far away. And in this way, Organic is trying to study our universe by using this gravitational lens. Now let's look at this image from James Webb Space Telescope. Focus in the middle where there is a galaxy cluster. That galaxy cluster is responsible for gravitational lensing in this image. This collection of galaxies and dark matter acts as a cosmic telescope for us, allowing us to see magnified and contorted images of individual galaxies, sometimes even mirror images of the same galaxy. You can see an example of this in this very image. On the left and right of the center, you can see some lensed galaxies in the orange arc. Here, the same individual galaxy is appearing twice in the arc. Look at this. The shape of this galaxy has also become elongated just because of gravitational lensing. Here, you can clearly see that the central part of the image is more affected by gravitational lensing, which may not look right to us visually, but otherwise, this part is also filled with scientific data. Not all galaxies have been mirrored in this gravitational field. Only a few galaxies are showing us this mirroring effect. Apart from this, some galaxies appear to be stretched and some galaxies seem to be interacting with each other. Here we can clearly see how Webb has refined a detail in this image. In this image, we can also find some galaxies that appear completely red, which would be among the oldest galaxies discovered by us. This image will take us even closer to the Big Bang, and gravitational lensing will help us see upcoming images in even more detail. James Webb Space Telescope is bringing a revolution in our understanding of the early universe. It is revealing those distant galaxies and the cosmic processes happening there to us in astonishing detail. But with every new discovery, it is also presenting us with some controversies and very big questions, especially about a very important era of the universe, the Reionization. Reionization is a very important time in our universe. Reionization is the time when the first stars and galaxies in our universe came together and completely changed the map of our entire cosmos. They completely transformed the universe. Since the Big Bang, our universe was going through an age, but the stars and galaxies together ended that dark age of our cosmos. It is believed that this dark age ended about 1 billion years after the Big Bang, but the recent data from James Webb Space Telescope has challenged this timeline. According to the latest observations from the James Webb Space Telescope, the era of reionization ended about 350 million years earlier than we had estimated. Because of this, questions are now being raised about the models we have created. Everything we've learned so far about the birth of this universe, are all those things just what we've assumed? The major theories that have been built on these models, are they all wrong? In today's video, we'll break down the reionization period and find out how. James Webb Space Telescope's discoveries are creating tension among cosmologists. And how can new theories help us explain these surprising results we're getting from James Webb Space Telescope? Is it possible that all the models we've created about the early universe are missing a lot of important information? Or have we always been making a big mistake in understanding this universe? Let's find out how James Webb Space Telescope can help us rewrite the rules of this universe. And what could this mean for the origin of our universe and for humanity? What are the rules of this universe? The reionization period is one of the most important periods in the cosmic history of our universe. This began about 100 million years after the Big Bang, when the first stars and the first few galaxies started forming in the universe. Those stars had started emitting intense ultraviolet radiation. It was so powerful that it was enough to break apart hydrogen atoms. This radiation broke those primordial hydrogen atoms into protons and electrons, and this process of reionization gradually spread throughout the universe. As a result, our universe went from a neutral state to an ionized condition. The universe, which used to be cold, had now become hot. Hydrogen is the most abundant element in our entire universe. That's why the changes that occurred in the universe during the reionization period were very profound, which was directly affecting almost 75% of the matter present in it. During this period, the gas present between the galaxies that were forming had become completely transparent. Because of this, light got a chance to escape, and during this time, light was able to travel freely in the universe for the first time. These changes were very critical because the galaxies we see today, this is what shaped those galaxies, those Milky Ways. And this has determined that these structures in the universe can grow rapidly. That means during the Reionization period, our universe started to take the shape that we are able to see today. This era of Reionization ended when all the hydrogen present in our universe was not completely ionized. And our astronomers believe that this phase lasted for about 1 billion years after the Big Bang. But recently, discoveries made by James Webb Space Telescope have revealed that the era of reionization ended much earlier than we had thought. The era of reionization had already ended between 550 and 650 million years ago. And if this is true, then our models of the early universe need to be revised on a large scale, and this could also become a big problem for us. These new results are exciting for us, but they are nothing less than a puzzle. When our astronomers first studied the Reionization period, they did so based on the cosmic microwave background, which is the afterglow of the Big Bang. And many studies were also done based on the Lyman alpha forest, which is a pattern of hydrogen absorption lines. When these two methods were combined, we got an idea that the period of reionization lasted for about 1 billion years after the Big Bang. But when JWST looked even deeper into the early universe, the surprise we got is something we are not able to place anywhere on our timeline. JWST's surprising findings. The James Webb Space Telescope has given astronomers the opportunity to look much deeper into the universe than ever before. We have never gone this far back in time before. James Webb Space Telescope has looked right into the heart of the Reionization era. And there we found things that were much more surprising, far more than we had ever imagined. Extreme ultraviolet emitting galaxies were present there. These bright and energetic galaxies are so powerful that they alone could ionize the entire universe. This challenges our belief that the process of ionization was a very long and slow process, and that it must have ended gradually over billions of years. This discovery tells us that the reionization period must have ended hundreds of millions of years earlier than we thought. Because the presence of those very bright galaxies in the early universe indicates that those galaxies themselves must have ionized the universe. But now the problem here is, if the reionization period ended so quickly, the cosmic microwave background and the Lyman alpha forest, both of these reliable cosmic indicators, appear different to us compared to today. Scientists are working to solve this, but still, if James Webb's observations turn out to be correct, then questions will be raised about the models we have created. So what could be the reason for this? One possibility is that in our current models, we might have missed some very important processes. For example, recombination, where ionized protons and electrons come together again. If recombination was happening much faster than we had thought, then at that time, extra ultraviolet radiation would have been needed to keep the entire universe ionized, which we have seen in James Webb Space Telescope's findings, and James Webb Space Telescope can explain this very well. The second possibility is that the early galaxies forming in the early universe were evolving much faster than we thought. As a result, they emitted a large amount of ultraviolet radiation into surrounding space. This means that whatever James Webb Space Telescope observed is an unexpected phase of cosmic evolution in our early universe. But until more data comes in, our scientists will continue to grapple with these astonishing discoveries. Because we don't have any tool available to verify James Webb Space Telescope's findings. Because this is the first time that we are able to look so far back in time into the universe. So we hope that when we get more data from James Webb Space Telescope, we will be able to form a solid opinion about this. Resolving the mystery. Between the data from James Webb Space Telescope and our previously established models, this difference tells us how little we actually know about the early universe. whatever debates are occurring in the scientific community due to this telescope's findings. For that, we need even more observations and better models that can help us understand how hydrogen recombined at that time and how galaxies evolved in the early universe. In the coming years, by combining the data we get from James Webb Space Telescope and future space missions, we will be able to clarify whether the results from James Webb are pointing towards any new physics, or maybe James Webb Space Telescope, especially James Webb Space Telescope astronomers. They are waiting for the data from the Euclid mission launched by the European Space Agency in 2023 and the future survey data from the Rubin Observatory in Chile, so that scientists can get some answers to this missing puzzle from there. However, along with this, astronomers are also re-examining our existing models to see if there is any flaw in our models themselves. For example, how much radiation was needed to ionize hydrogen? Was it less or more than the value we predicted? Are we wrong here? Meanwhile, some scientists believe that recombination must have played an important role in this process, which we have ignored in our models. Some scientists also speculate that the formation of the first stars in the early universe, they were extremely large and very powerful, and because of them, the process of reionization became much faster. But one thing is certain. JWST has opened a new chapter in our exploration of the universe, and the debate about reionization will continue for years to come. Julian Munoz and his colleagues are working on this cosmic mystery with the hope that when new data arrives, they will finally be able to uncover the true timeline of reionization and take a step forward in solving this cosmic mystery. Whatever answers we get from future discoveries, they will not only reset our understanding of reionization but also our understanding of this universe. In fact, they will also strengthen the foundation of our modern cosmology even more. This is a very exciting time for scientists. Every observation being made with the James Webb Space Telescope is bringing us even closer to the true nature of this universe. We are now able to truly understand it. And seeing this, it seems that James Webb is proving to be completely successful in its mission. Conclusion: the results obtained from the James Webb Space Telescope have sparked a new scientific debate which could change our understanding of the evolution of our universe. If reionization ended earlier than what our previous models predicted, then it challenges all those models and ideas that we had developed based on those models, like how the first stars and galaxies were formed and how they contributed to this process. These discoveries show how little we know about the early universe and how much we still have to learn. As Julian Munoz explained, this is not just a matter of one or two galaxies changing, but a question of the evolution of the structure of the entire universe. What happened is true, but neither we nor our models ever predicted this, yet it happened within our current models. To resolve this tension, scientists need to work on even more detailed observations and new refined theories. With more missions like the Euclid mission and data from Robinson observations, we can try to solve the mystery of reionization. But until then, the James Webb Space Telescope will continue to challenge our old ideas and open up new paths for discoveries. This journey to uncover the mysteries of the universe has only just begun, but one thing is certain: we humans have never fully understood the universe. This is just the beginning of those astonishing discoveries. We still have a lot to learn from JWST. James. The Webb Space Telescope has discovered a planet that is completely surrounded by silicate clouds. Those clouds are constantly swirling in the planet's atmosphere. Hot clouds sometimes rise, while cold clouds sometimes sink. Its atmosphere is changing every moment. It's completely unstable. Scientists believe that the new planet we've discovered was born just now on a cosmic scale. We have discovered a newborn planet, and we've also received some very surprising data from it, which we are going to talk about in today's video. The James Webb Space Telescope has been continuously working to solve the mysteries of this universe since 2021. When this telescope began its operations, the first few images and data that came out from it were remarkable. Seeing that, scientists understood that this telescope can show us things we can't even imagine. And recently, something similar has been observed. They are studying the data from James Webb. Researchers have found a planet that is orbiting not just one but two stars. This planet, named VHS 1256b, takes about 10,000 years to orbit these two stars. However, a day on this planet lasts just 22 hours. This binary star system is located about 40 light years away from our sun, but all these things don't make it as special as the processes happening on this planet, which really make us think. This entire planet is currently a gas planet. Why did I say currently? You'll find out later in the video. Scientists mainly observe silicate clouds on this planet, which are constantly moving around here and there. On this planet, sometimes hot material rises up and sometimes cold material moves downward. Just think of it as a massive storm raging across the entire planet, which is much bigger than the Great Red Spot Storm on Jupiter, the largest planet in our solar system. Because of this, we are seeing very dramatic changes in the brightness of this planet as well. Scientists say that this is the most variable planet ever observed, which is changing its brightness so quickly. Along with this, scientists have also detected the presence of water, methane, and carbon monoxide on this planet. It was possible for James Webb to do this, and perhaps James Webb also got a kind of advantage from the position of this planet. It was possible for James Webb to do this, and maybe Webb also got an advantage from the position of this planet. It was possible for Webb to do this, an advantage for James. For Webb, being able to do this was also an advantage. Being able to do this in a way, who knows? By then, whether humans will even exist or not, that can't be said. But with this complex data from Webb, we've taken a snapshot of a planet in the universe that's repeating the past of our solar system. In the future, if we humans develop enough to be able to do interstellar travel, then finding such destinations becomes very important for us, where we humans can live from the beginning so that we get time to live and evolve there. And we all know the reason for leaving here, that our sun will destroy everything from our Earth to Mars in the coming few billion years. It will become a red giant, and this planet could be a new Earth for us, friends. Scientists believe that this planet, which is surrounded by such dense clouds today, will be totally calm after millions or billions of years. And its atmosphere will become fully transparent like Earth's, where life could possibly flourish again. This is just the beginning for James Webb. This telescope is going to reveal even more deep mysteries of the universe to us in the coming times. Friends, how did you like this information? And if this planet becomes suitable for living in the future, should we go there? Share your opinion in the comments. Friends, for such informative videos, make sure to subscribe to the channel and enable the bell notification. Friends, we'll meet again soon with another fun episode. Until then, stay curious, happy, and goodbye. Goodbye.